Hello everyone, welcome to my lecture. Here, let's have a discussion about continuous functions. Continuous functions. You can see the definition here. Let x d1 and y d2 be two metric spaces. These are two metric spaces. Metric spaces we have already discussed. That. Okay. In one of our previous videos. So we suppose we have two metric spaces here. First one is x d1, second one is y d2. Okay, that means the first set is x whose metric is d1 and the second set is y whose metric is d2. Okay, if you have any doubt in metric spaces, you can check my previous videos. So suppose we had two metric spaces like that, and f from x to y. Suppose we have a function that is from the first set x to the second set y. Then f is said to be continuous at a point x naught belongs to x. When can we say that this function is continuous at a point x naught in x? If for every epsilon greater than 0, there exists a delta greater than 0 such that d1 of x naught less than delta implies d2 of f of x naught less than epsilon. Okay, if this satisfies, then only we can say that this function f is continuous at this point x naught. Okay, so we have two metric spaces. First one is x with metric d1 and second one is y, capital Y with metric d2. And we have a function from x to y. When can we say that this function is continued at certain point, at a point? Suppose that point is x naught. If it satisfies this condition. If it satisfies this condition. If it satisfies this condition. For every epsilon greater than 0, there exists delta greater than 0 such that d1 of x comma x naught less than delta implies d2 of f of x comma f of x naught less than epsilon. If this satisfies, we can say that that function is continuous at a point x naught. Okay, in this case, we can say that that function is continuous at a point x naught. Okay, so for any epsilon greater than 0, okay, for any epsilon greater than 0, you should find a delta, okay, which satisfies this statement. Then only we can say that that function is continuous at that particular point x naught. Okay, we will discuss some examples. With that examples, you will get a better clarity regarding this. So this is the definition of continuous function. So if it satisfies this statement or these inequalities, we can say that that function is continuous at this point x naught. Now imagine if it is continuous at all points in this capital X, not only at x naught, not only at one point, not only at one or two points. If it is continuous like this x naught at all points of our domain x, then we can say that that function is continuous on this entire domain x. Okay, so that is the definition of continuous function. Okay, this means continuous only at one point x naught. But if this condition for x naught that is happening for all the points in x, not only at this point x naught, not only at one or two points. If this condition is satisfying at all the points in x naught, all the points in our domain, which is our domain, this one, capital X, then we can say that that function is continuous in that entire domain x. Okay, so such functions are known as continuous function. Or we have another definition here. We have another definition. This is one definition and another definition. Continuous function can be defined in this way also. You can see here. Continuous function can be defined in this way also. You can see here. For all epsilon greater than 0, there exists delta greater than 0 such that x belongs to, this means open ball. Okay. Open ball centered at x naught and radius the delta. Okay, implies f of x belongs to another open ball, okay, or another open circle whose center is f of x naught and radius epsilon. Okay, both are equivalent definition. Okay, we saw the first definition here. and this is the second one. Both are equivalent. Okay, let's see how can we say that both are equivalent. I will show that. Let's take a new page. So first definition says that, see, suppose you have suppose this is the point x naught. Okay, this is the point x naught in our domain capital X. Okay, this is the point x naught, and we have an open ball around that. Okay, we have an open ball, or we have an open circle around that, whose radius is delta. Okay, whose radius is delta. What will happen if you take any point inside this circle? If you take any point, suppose you are taking a point x inside this circle, then the distance between this x and this x naught is always lesser than this delta, right? Because delta is the radius. Okay, delta is the radius. If you take any point inside this circle, the distance between that point and x naught is always lesser than that radius, right? It's always lesser than that radius. Okay, so if you take any point inside this, if you take any point inside this circle or inside this ball, that means the distance between that point and the center x naught is less than delta. Okay, so we can say that this x, see, this x belongs to our ball whose center is x naught and radius is delta. Okay, this means what? Our point x is inside this ball or inside this circle. That is same as saying what? That is same as saying the distance between d1 is the metric here. Okay, so the d1 of x comma x naught is what? Less than delta. Both are equivalent statement, right? Both are equivalent statement. Okay, if x is inside this ball or if x is inside the circle, that is same as the distance between x and x naught is less than delta, because the radius of this ball is delta. If x is coming inside, the distance between that x and x naught will be less than delta. Okay, that's what you can see here. See here. Okay, so here this says what? The distance between that x and x naught is less than delta. Here it says that x belongs to that open ball. Both are same only, right? Both are same. Okay, other part also you can see. See, d2 of f of x naught less than epsilon. Here it says f of x belongs to what? Another open ball whose center is f of x naught and radius is epsilon. Same only. You can see here. This is our first metric space. This is our domain X. Now take the second metric space, our codomain Y. Y. Okay. So f is a function from X to Y. So X naught belongs to this X. Okay, capital X. So f of X naught belongs where? Belongs to where? F of X naught belongs to this one. Suppose this is that f of X naught, this point. Okay. And let's take a circle, or let's take an open ball around this point, with this point f of x naught as center. Okay, and whose radius is what? Whose radius is epsilon. Okay, now if I take any other point f of x that is inside this circle, what does it mean? It means the distance between this f of x and f of x naught is less than this epsilon, right? So if I say that this f of x belongs to this ball whose center is f of x naught and the radius is epsilon, that is same as, that is equivalent to saying what? The distance between here d2 in y, the metric is d2. Okay, the distance between that point f of x naught and f of x is what? That is less than epsilon. Both are same only. Okay, that is what you can see in the second part here. Okay, these two are same only. F of x is belongs to that ball. That is same as saying that the distance between f of x and f of x naught is less than epsilon, the radius of that ball. Okay, so both are. So continuity you can define in both of the ways. Okay, you can check continuity of functions using any of these ways. Okay, let's see some examples here. Some examples of continuous function. Here you can see the first example. Okay, here you can see the first example. This is the first example. This is the first example. Identity function f from x to itself. Okay, suppose you have a function f from a metric space x to x itself, defined by f of x equal to x for all x belongs to x. Okay, this function is known as what? This function is known as identity function. Okay, because the value of the function is the value of x itself. This function is continuous. This function is continuous. We will prove or we will show that this function is continuous using this definition of continuous function that we have discussed here. Let's see how can we say that this function is continuous using our previous definition. According to our definition, this should be satisfied. Okay, all right, this should be satisfied so that the function becomes continuous. For all epsilon greater than 0, there exists delta greater than 0 such that d1 of x comma x naught less than delta implies d2 of f of x comma f of x naught less than epsilon. This should happen there in our example. Then only we can say that that function is continuous. If it is violating this rule, we cannot say that it is continuous. Okay, let's see how can we prove this. So for all epsilon greater than 0, for all epsilon greater than 0, that means if you take any positive number as epsilon, that's the meaning of for all epsilon greater than 0. This should happen for any positive number. You can take, you have to prove this for any positive number. You can take this epsilon as any positive number. It should be true for any positive real number as epsilon. Okay, if it is not true for at least one epsilon that is positive, then we cannot say that it is continuous. Okay, so it must happen for any epsilon greater than 0. Okay, yes. So first we need to take what? First we need to take such an epsilon. Okay, that's what you can see here. That's what you can see here. Let epsilon greater than 0 be given. Suppose you have such an epsilon. Okay, suppose you have such an epsilon. Then we will prove what? Then we will prove this condition is satisfied. This condition for continuity is satisfied for that epsilon. But that epsilon is arbitrary, right? We did not mention which is that epsilon. This is arbitrary. Okay, so it is true for an arbitrary epsilon means it is true for all positive numbers. Okay, so we are taking an arbitrary epsilon positive. We will prove that this condition for continuity is happening for this arbitrary epsilon. That means it will happen for all positive value. You can take any positive value for epsilon, it will always be true. That means it is that function is continuous. Okay, yes. So let epsilon greater than 0 be given. Then what we need here to prove that this function is continuous, we need to find a delta greater than 0, right? That is what our definition says, right? For all epsilon greater than 0, there must be a delta greater than 0. Okay, so if you take any positive epsilon, you should find a delta that is positive. Okay, yes. So what we need to find here? We need to find delta greater than 0 such that it should satisfy this condition. Okay, d of x comma x naught less than delta implies d of f of x comma f of x naught less than epsilon. In our definition, we have taken d1 and d2. Okay, d1, d2, because these are different metric spaces. First one is metric space x whose metric is d1. Second one is metric space y whose metric is d2. Different metrics. That's why d1 and d2. Okay, but here this function is from x to itself. So no need to take as d1 and d2. We can take a single metric. Okay, because the function is from x to itself. So no need to take separate d1, d2 metrics. Both the metrics are same only. Okay. So that's why no differentiation between d1 and d2 here. Here d, here also d. Okay. So we need to find such a delta greater than 0 that satisfies this condition. Okay. We can find such a delta. Okay. So let epsilon greater than 0 be given. We have such an epsilon. For this epsilon, we need to find a delta. For any epsilon like this, we can find a delta. Just choose delta is equal to that epsilon. Okay, suppose our epsilon is 1, then take delta also as 1. Then it will satisfy this condition in this function. Okay, yes. So if suppose your epsilon is 0.5, choose delta also as 0.5. You can see this condition there. Okay, suppose your epsilon is 0.1, take delta also as 0.1. Suppose your epsilon is 0.001, take delta also as 0.001. Okay, That means for any positive epsilon, for any epsilon greater than 0, you can always find a delta with that. Just choose delta as that epsilon itself. Then you can see this condition satisfied. Let's see how that condition is satisfied if you take delta equal to epsilon. See here. That means d of x comma x naught. That means the distance between x and x naught less than delta implies what? D of x comma x naught less than epsilon. Because we have taken delta equal to epsilon. So delta less than delta means less than epsilon. Okay. That means what? D of f of x comma f of x naught less than epsilon. Because x is what? X is f of x. And x naught is what? X naught is f of x naught. That's how we defined our function. F of x equal to x only. Okay. So f of x naught is x naught itself. That's what you can see here. F of x and x are same. So instead of x, you can write f of x. Similarly, instead of x naught, you can write f of x naught. See, that means d of f of x naught less than epsilon. That is what we need to prove, right? Okay. So this will happen for any epsilon greater than 0. For any epsilon greater than 0, you can always find a delta that is equal to that epsilon, which satisfies this condition. Okay. Which satisfies, yes, this condition. Okay. So that means this function, okay, this function, identity function is continuous at a point x naught. Okay. But what is this x naught? X naught is an arbitrary point. Okay. Okay. X naught is an arbitrary point in our x. So that means if it is true for x naught, it is true for any point in this x. That means this function is continuous throughout this x. All right. Let's move to second example. I have another example for you. This function, you can see here, this function. You can read that function here. This function. This function is also continuous. Using same definition, we can prove. Using same condition, we can prove. You can read here. Let x d1 and y d2 be two metric spaces. Here we have two different sets. First one is capital X, that is domain with metric d1, and second one is capital Y, that is our codomain with metric d2. Then for any fixed c belongs to y, take any fixed number, okay, and denote it as c belongs to y. Okay, then the function f from x to y defined by f of x equal to c for all x belongs to x, and we know that this function is known as constant function. Okay, f of x equal to a constant. Okay, no matter what is the value of x, f of x is always that fixed number c, that fixed value, that fixed element c in our y. Okay, that function is known as constant function. That function is also continuous. Okay, that function is also continuous. We can prove this. We can prove this by the same method using the definition. Okay, how can we prove that this function is continuous? Let epsilon greater than 0 be given. Okay, the definition of continuity is like that. Okay, for all epsilon greater than 0, we need to find a delta greater than 0 such that d1 of x comma x naught less than delta implies d2 of f of x naught less than epsilon. Okay, the distance between x and x naught, if it is less than delta, then the distance between f of x and f of x naught will be less than epsilon. This will happen for any epsilon greater than 0. Okay, for any epsilon greater than 0, you will always find the corresponding delta. Okay, suppose we have that epsilon. That epsilon can be any positive number. It's an arbitrary element. Okay, if you can prove this is true for that arbitrary epsilon, that means it is true for all positive numbers. So epsilon can be anything positive. Okay, suppose we have such an epsilon, then we need to find what? We need to find the delta corresponding to that epsilon such that it satisfies this condition. Okay, but here interestingly, you can choose any positive number as delta. Okay, you can choose any positive number as delta. Okay, in the previous example, we have chosen delta equal to epsilon itself. Okay, but here, no need of choosing like that. You can choose delta as any positive number. Why? Why is it you can choose delta as 1? Then you can see this condition will be satisfied there. This condition will be satisfied if you choose delta as 1. You can choose delta as 2. Then also you can see this condition is satisfied there. I will show you why. You can choose delta as 100. Then also you can see this condition is satisfied. If for any, you can choose any delta. Because, see, what will happen if you choose any delta? what will be this value? D2 of f of x naught. That means the distance between f of x and f of x naught will be equal to what? D2 of c comma c. Why c comma c? Because f of x is always c, f of x naught is always c. For any value of x, f of x is always that constant, that fixed value c belongs to a. That is always fixed, constant function. Okay. So f of x is c, f of x naught is also c. What is the distance between c and c? If the distance between the same point is always 0. Okay. So d2 of the distance between c and c is 0. 0 is always lesser than any positive epsilon, right? Epsilon is positive. It can be any positive number, but it is positive. Positive means it is always what? Greater than 0, or 0 is always lesser than this epsilon. This will happen for any epsilon. This will always happen no matter which delta you have chosen here. This condition, f of x, the distance between f of x and f of x naught is always 0. That is always lesser than any positive number. So you are free to choose any delta. Okay. For infinite delta axis, if you choose any epsilon, because this is always less than epsilon. Okay. So this function is continuous at an arbitrary point x naught. Okay, this function is continuous at an arbitrary point function x naught. If it is continuous at an arbitrary point, that means that function is continuous throughout the domain. Okay, let's stop here. I hope it's clear. We'll meet you in the next video. Okay, thank you.